Let's look at sketching rational functions. A lot of times you'll see a chart like this that I need you to fill in for finding what a graph of a rational function looks like. Suppose I have the function y is 2x squared minus 9 divided by x squared minus 4. The first thing you always want to do is find the first derivative. So f prime of x is 20x divided by x squared minus 4 squared. The next thing you want to do is find the second derivative, and the second derivative of this function is f double prime is minus 20 times 3x squared plus 4 divided by x squared minus 4 cubed. Now you'll see I'm going to be color coding things for a reason. Let me look at the x-intercepts. The x-intercepts, you remember, are where they cross the x-axis. And where does it cross the x-axis? Well, it crosses the x-axis when y is 0. So y equals 0 when the numerator is 0, or when x squared minus 9 is 0, or when x is equal to plus or minus 3. So the x-intercepts are at x equal negative 3, 0, and x equal positive 3, 0. Now let's look at the y-intercepts. The y-intercepts occur when x is 0. So when x is 0, what does y equal? Well, that's 9 times 2 divided by 4, or 9 halves. So the y-intercepts occur at the point 0, 9 halves. Now let's look at vertical asymptotes. The vertical asymptotes occur when the denominator is 0. So the vertical asymptotes occur when x squared minus 4 is 0, or x equal plus or minus 2. So these are the equations of my vertical asymptotes. X equals plus 2 and x equals minus 2. For the horizontal asymptotes, we need to take the limit as x approaches infinity. In both the positive and the negative direction, but in this case it turns out it doesn't matter. In both of these cases, it is 2. So I have a horizontal asymptote of y equals 2. Now let's look at the end behavior. The end behavior for this one is that it follows these horizontal asymptotes at y equals 2. It does not become unbounded. Let's look for our critical numbers. Our critical numbers occur when, and I'm going to move down here a little bit, our critical numbers occur when the first derivative is 0. So I'm just going to use Cn. And the critical numbers are when y prime equals 0. Now where does y prime equal 0? Well, it equals 0 when 20x equals 0, or x equals 0. So my only critical number is x equals 0. What are possible inflection points? Possible inflection points occur when the second derivative is 0. Okay? Now, it turns out f double prime can never equal 0 because, let's look at the numerator. The numerator can never equal 0. So there are no possible inflection points. Let's look at the domain. The domain is all real numbers except where our vertical asymptotes are, x equal plus or minus 2. And now for our test intervals, I want to come back up to my chart. These do take a while, don't they? So back up at my chart, from negative infinity to negative 2, I don't really care what the first derivative is, and I What do I know between negative infinity and negative 2? I know the first derivative is negative, and I know the second derivative is negative. So I know it's decreasing because the first derivative is negative, and I know it's concave down because the second derivative is negative. Now we do need to look at x equal 2. At x equals 2, f of x is undefined, f prime is undefined, f double prime is undefined, and this is a vertical asymptote. Between negative 2 and 0, f prime is negative, and f double prime is positive. So it is decreasing, but concave up. At x equals 0, what happens at this endpoint? At x equals 0, I know f of x is 9/2. So I have a point that, oh, I put it in the wrong place. Sorry about that. It's 9/2. So I have a point I can graph. F prime at this point is 0, and f double prime is positive, which tells me I have a relative min. So now at this point in time, I know from 0, 9/2 to negative 2, it's a relative min, and I know it's decreasing and concave down, so I know I can sketch this part right here. I'm going to go back and sketch that part up there. Between 0 and 2, what do I have? Between 0 and 2, I know the first derivative is positive, and the second derivative is positive, which means it's increasing and concave up. So I start at this point right here, and I keep going up. Now at x equal 2, f of x is undefined, so I'm going to put a big X there. F prime is undefined, and so is f double prime. And this is a vertical asymptote as well. So I can come in and put this right here as my vertical asymptote. Just as I should come in here and put in negative 2 is a vertical asymptote. And finally, let's go to between 2 and infinity. I see that my first derivative is positive and my second derivative is negative, so it's increasing and it is concave down. All right, so as soon as you have all of this information, let's go back. Between negative 2 and infinity going this way, I do have a point in that region, and that's negative 3, 0. So as soon as I sketch that point in, and I see that it's decreasing and concave down with a vertical asymptote at y equals 2, I can do this sketch right here. I've already done the middle part. I come over to 3, 0, and I see that that is also a 0, but in the region between 2 and infinity, I am concave. Now that was in pink, I don't want to do that. That was increasing and concave down. So I get this sketch right here. You can see, using all of these skills, we can be very careful and get very precise in some of our sketches.